When scientists measure energy, there are different kinds of units that are used, and we need to do a little bit of history here. One of the first types of units of energy that was used was called a calorie. And calorie, which this, by the way, has a small c for calorie, is the heat required to raise 1 gram of water by 1 degree Celsius, all right? And this was one of the first types of science units that were used. James Joule there on the right-hand side, he was one of the first great thermodynamicists. He did a lot of these studies. I believe he was the one that suggested the calorie per unit, but I'm not totally sure. However, notice that calorie there is a small c. 1,000 of these calories is a kilocalorie. So just like 1,000 meters is a kilometer, 1,000 calories is a kilocalorie. And kilocalorie is usually abbreviated as kcal. And 1 kcal is equal to 1 calorie with a capital C. And sometimes people will call this a food calorie. So if you're used to reading labels when you go to the store for the calorie content of foods and stuff you buy, the calories they mention there are the kilocalories, the capital C calories. It's not what I call the science calorie, the little tiny c. So it's very, very frustrating. Small c calorie is 1 gram of water by 1 degrees. That's the energy. But big C calorie, the food calorie, is equal to 1,000 of those calories, and it can get pretty confusing. So in our science world, we're going to use what's called the joule. And the joule is the SI unit. It's the official unit of science, all right? And joules, which are usually capital J, but you can spell them with a little j, which I know is confusing, named after James Joule, is going to be an important thing. Joule is called a derived unit. It's equal to a kilogram meters squared per second squared. We'll talk about later why that's important. But for right now, what I'd like you to know is that 4.184, that's the number of joules in a science calorie, all right? So that's science calorie. So there'd be 4,184 joules in a food calorie. And you can also have kilojoules, which would be 1,000 joules, stuff like that. This 4.184 number, pretty important. So memorize it. Make sure you know it. We're going to use it a lot and stuff this section. And I only want you reporting energies in joules. Don't use the science calories or the food calories or kilocalories. There's other kinds of units of energy like ergs, all right? And maybe in other classes they will be helpful. But in this class, make sure that you use joules and kilojoules, stuff like that. And that 4.184 number is going to come back to help us a lot, as we'll see. Thermodynamics revolves around what's called the law of conservation of energy. And the law of conservation of energy just says that the total energy is unchanged in a chemical reaction. And what that means is you basically cannot create or destroy energy. All the energy that goes in equals all the energy that comes out. It sounds a lot like the law of conservation of mass, and there's a reason for it. We'll see later. But anyway, yeah. So the total energy doesn't change. You don't create or destroy any energy. Of all the forms of energy that are used in science, the two that are important are what are called heat and work. And heat gets the symbol Q, work gets the symbol W. So the way to express the law of conservation of energy in terms is you would write delta E equals Q plus W equals 0. And this is what they call the first law of thermodynamics. Now, in this rule, the heat, which is energy absorbed or released, plus the work, the work done by a system, all of that together has to equal 0. And there's lots of implications for this. So what I'd like you to get first of all is that the first law of thermodynamics just says that you're not going to create or destroy any energy. You can rearrange the energy, like eating the gummy bear will transfer the gummy bear's energy into you, but you're not like creating energy, you're not destroying any energy, it's just being dispersed in different ways.
Heat, or thermal energy, is associated with the motions of atoms and molecules in a substance. The more rapid these atomic scale motions, the greater a substance's thermal energy and the hotter it is. When we plunge a hot metal bar into cool water, thermal energy from the bar transfers to the water. While the atoms and molecules of the bar slow down, those of the water speed up. The transfer of energy can be measured as a rise in water temperature.
Molecules of a hot substance move more rapidly than those of the same substance with a lower temperature. If the two samples come in contact, a transfer of molecular momentum occurs from the rapidly moving molecules to the slower ones. In this way, thermal energy transfers from the hotter sample to the cooler one. When the two samples have similar rates of molecular motion, they have reached thermal equilibrium and have the same temperature.
I'm going to state this, even though I bet it's pretty obvious to you, but it's a really important part of thermodynamics. When it comes to heat, if you put something hot with something cold, the heat from the hot is transferred to the cold species, and at the end, both species will be at the same temperature warm. There are no examples of hot and cold coming together, and the hot gets hotter and the cold gets colder, all right? Always hot plus cold equals warm. And you can see in the lower right-hand corner there an example of that. A hot and a low temperature sample come together. The heat is transferred, the thermal energy from the hot to the cold, and at the end you end up with two essentially warm species. And you can tell in that video in the middle there that yeah, hot was moving pretty fast, cold was moving pretty slow, and at the end those purple atoms are warm. In thermodynamics, they often talk about if heat energy is given from the system to the surroundings, or if surroundings have to give energy to the system to make a reaction occur. So two terms we're going to use a lot are called exothermic and endothermic. And in this slide, we're looking at exothermic. So in an exothermic reaction, heat is given by the system to the surroundings. So what happens is the reactants react, they release a lot of energy, and maybe the water around it, or maybe the air molecules around it, or the container, whatever, all of those things absorb the energy. So that's why it's an energy transfer. It goes from the inside to the outside. If you were to measure the temperature of an exothermic reaction, the temperature will go up because the temperature that's being measured is the surroundings. It's almost impossible to measure the system, but the surroundings you can measure, the solvent, the water molecules around it, the air, whatever. So if you do a reaction and the thermometer increases, gets warmer, that means you have an exothermic reaction. Let's say that you have a reaction and the reaction feels warm upon completion, and you didn't use like a hairdryer to warm it up or something like that. How would you describe it? Exothermic, endothermic, neither, or do you need more information? And obviously, if the reaction feels warm upon completion, this is going to be exothermic. So if you do a reaction and it feels hot after the chemicals react, exothermic. Energy was given off by the reactants. The system gave off energy to the surroundings. Kind of cool. Well, not literally. It's actually pretty hot. But thermodynamics joke. I know, get a day job. On the other hand, you can have an endothermic reaction. These aren't as common, but they do happen. And a great example of this is a cold pack. Sometimes when if you do sports, there's an injury, and they'll apply a cold pack to the place that was injured. It's something that when you activate it, it feels really cold. So in these cases, you have an endothermic reaction. The outside has to give energy to the inside, or in these kind of terms, the surrounding donates its energy to the system in order to make the reaction happen. So if you were to measure the temperature of this, then the temperature will actually go down because, again, thermometers usually measure the surroundings, not the system itself. Ice melting is a great example of this. If you let ice lay out in the temperature above the freezing point of water, absolutely the ice cubes will melt. It's absorbing the energy from the outside to melt the ice cubes and turn them into liquid water.